Hey guys, today we're going to be doing an exercise called Safe to Launch, in which you're seeing if a C-130, a cargo airplane, is properly loaded and safe to go flying. And to do this, we're going to use our knowledge of torque. So this is an application to these concepts of torque that we've been learning here as we've been going along. So before we get into the specifics of this, I need to give you the big picture of how we approach this sort of a problem. So let's go over to, here we go. All right, so we're going to start off by reviewing something that we did just after the torque lab, where we had our meter stick hanging from the second hole, and we had a weight hanging from the short end, and in this example I have a weight hanging out here on the far end too, but the goal of this was to determine the mass of the stick. Okay, it's a problem we did in class, and I also made a short video on it for the folks at home. So we're going to start off by reviewing that and doing that again, and then we're going to build on that. So if you want to pause the video at this point to solve it for yourself, as review, go for it. I'll go through it and we'll see what the answer is. Now remember, the stick itself behaves as if all of the mass is at the center of the stick, which is at the 50 centimeter point. Okay. Okay, so the way we do this is we use distances from the balance point. So we have 650 grams times 0.1 meters, that's to the right, and that is equal to, excuse me, 50 grams times 4.4 meters, plus the mass of the stick. We're going to call that M. M times 3 holes, so 0.3 meters. Okay, and then we just solve this for M. So we get 65 is equal to 20 plus 0.3 M. There we go. And so we get 45 is equal to 0.3 M, and that means that M is equal to 45 divided by 0.3, and we get 150 grams. Okay, so this is 150 grams for the mass of the stick. That's what we get. Okay, now we're going to take this a step farther, and what we want to figure out is where is the center of mass, find the center of mass for the stick and the weights. So for the whole contraption, the stick plus the weights, right? So the stick has 50 grams hanging here and 650 grams hanging here. And we want to know, if we look at that as a whole system, the stick plus the two weights, where is the center of mass of that entire thing? All right. So the way we do this is sort of like a Planck problem. We're going to be doing the same thing. We're going to use a reference point here. Let's go from this end. Why not? Okay, so this is going to be our reference point. And remember, we're going to be looking at the torques, the individual torques for each one of the items here. And then we'll figure out the CG from it. Okay. So it's kind of a bookkeeping exercise, but we'll take them in turn. So we have 650 grams times 0.1 meters. That's this one. The stick itself is going to be 150 grams times 0.5 meters. And then the little weight out here is 50 grams times 0.6 meters. Those are all meters. We'll figure out the torque produced by each one of those, and then we're going to add them up. So this comes out to be 65. This comes out to be 90. Let's see, 75 rather. That's not a 0.65, that's 65. This is 75, and then the last one comes out to be 30. Okay. Now we add them all together. So what we're doing when this is the mass. This is the radius or the moment arm, and this is the torque. So we have our torque equation. Torque is equal to mass times the distance, the radius that goes out here. So the total torque comes out to be 65 plus 75 plus 30, 170 units of torque. And our total mass comes out to be 650 plus 150 plus 50, 850 grams. Okay, so this is where we're stepping forward a little bit. We figured out the total torque acting on this system, and we know the total mass. And if we know the total torque and we know the total mass, we can figure out the distance to the center of mass, the point where it behaves as if all of that mass is located. Okay, so we will, to figure this out, the radius, we're going to do, I'll draw this out here so we can see it. So torque is equal to the mass times the radius. The total torque is 170, and that is equal to the mass, 850, times the distance from the pivot point. So we need to divide 170 by 850, and we get radius is equal to 0.2 meters. Okay, so what we've just figured out through this method here is that the center of mass of the stick and all the weights is 0.2 meters from the end of the stick. Now, maybe you're surprised that it happens to come out right from the that the center of mass is right where the suspension point is, because this is where we hung the thing up. But if you think about it for a minute, not really. It shouldn't be surprising, because that's where the center of mass has to be for this thing to balance. Imagine that the center of mass was over here. Okay, in other words, what we're saying is that the whole 850 grams behaves as if it's hanging from this particular point, which means that all the weight is hanging directly underneath the suspension point, and that's why it bounces. Now imagine that that center of mass was over here someplace. Well, what would happen is the stick would swing down like this, so that the center of mass was underneath the suspension point. And likewise, if the center of mass was over here someplace, then it would swing this way again, so that the center of mass swings underneath the suspension point. But this process of deriving where that center of mass is, this is what we need to be able to do to solve the airplane problem. Okay, and just to review what we've done, we've chosen a reference point, happens to be the end of the stick in this case, and we've calculated the individual torques contributed by each piece of the whole thing. So 650 grams was 0.1 meters. The 150 grams, the mass of the stick itself, is 0.5 meters from the end of the stick. And then this extra weight out here was 0.6 meters from the end of the stick. We get a torque for each one. We add up the total torque, and we divide it by the total mass, and that gives us the location of the center of mass of the entire stick. Okay, that's the process we'll go through. Now let's go back to the, take a look at the handout here. Here we go. So yeah, this is a C-130. It's a big cargo plane. Not a huge cargo plane, but it's a big one. On the back page here, the second page, I have a diagram so you can kind of visualize what's going on. Flying a C-130 is like going away for the weekend and never leaving your garage. It's this big open cavernous bay that you can pull vehicles into, and then we tie them down to the floor and carry them wherever they need to go. So this is to help you visualize. So you can just park them wherever you want them to be, and that's where you are. So it's possible to move these things around. That's the point. These ones are all fully loaded, but if like we only had 3 vehicles in this plane, we could move them forward or backwards and set them wherever we want to make the balance work out. Okay, and making the balance work out is very, very important when you're flying any airplane, not just cargo airplanes. Because when you think about it, the airplane, as you know, it's the wing on the airplane which produces the lift. So it's as if you've taken this airplane and you're hanging it from a string which is tied to the wing. So the center of mass of the entire plane has to be underneath the wing. If it's not, if the center of mass, center of gravity, center of mass was farther forward, then the nose would drop so that the center of mass was underneath that wing, because that's what's holding the whole thing up. And it doesn't fly very well if the nose is pointing at the ground and you can't bring the nose up. And likewise, if the center of gravity is too close to the tail, then the nose will pitch up as the weight tries to hang underneath the wing, and then you stall, and again, you have a short and unpleasant flight. So it is incredibly important to make sure that the center of gravity of the entire plane is under that wing. And that's your task in this assignment here. Okay, so the center of gravity has to be between 40 and 47 feet behind the nose of the airplane. We use the nose of the airplane in this problem as our reference point, and we measure the torques relative to that point. And there's many things that are loaded in the airplane. First is the plane itself, and that's like the stick. The meter stick has a center of mass, and we know where it is. Well, the plane has a center of mass also. So the plane itself has a mass of 75,000 pounds. So all these numbers here are in thousands of pounds, and it's totally okay to just leave them in terms of thousands of pounds. And the center of gravity of the airplane itself is 40 feet behind the nose of the airplane. Okay, so that's like the stick. Then we have fuel, because you have to have fuel to make the thing go flying, and the fuel is in tanks in the wing, and we put on 45,000 pounds of fuel, and it's 42 feet from the nose of the airplane, so it's stored in the wings. Then there's a truck that weighs 30,000 pounds, and it's 27 feet behind the nose of the airplane. And then we have 4 big cargo boxes, 4,000, 5,000, and 6,000 pounds, and these are their locations. They're farther and farther back. So to visualize this, it's like we have a truck up here near the nose, and then 3 boxes stacked out behind them. Okay, and that's the locations. And it's all in this table here. So your task is to figure out the individual torques and figure out where is the center of gravity of the entire plane, the plane itself with all the cargo and all the fuel, and see if it falls within these limits for where the center of gravity has to be. Okay, now I've put this in bold so you don't miss it. You need to make sure that the center of gravity is going to remain within safe limits for the entire flight, from the time we take off to the time we land. Okay, and you may be saying, well, what's the big deal with that? Well, of these things that are on this list here, are any of these going to change as we fly across the Atlantic Ocean for 10 hours? Okay, and without too much thought, I think you'll see the fuel weight's going to change because we burn gas. And that means that this weight is going to change, and this line is going to change. And you need to make sure that the CG is going to stay within those safe limits, even as we're burning fuel. Okay? And if it's not, then you need to come up with some plan for what to do about it. All right, you're basically the load master. That's a very important position on an airplane, is the person who's in charge of how things are loaded and where they're loaded. Everyone's life is in that person's hands, and you're going to be the load master on this one, but not with real airplanes, so don't feel too much pressure. Okay, so that's what we're trying to do. Yeah, I'm going to let you go with it. I think that's enough to get you going. You're going to write a short memo to the boss saying whether we're safe to launch or not. If we are, show the numbers to show that we're safe to launch. If not, then make a recommendation for what we might be able to do so that maybe we can be safe to launch. Our best choice, what we want to be able to do, is carry all this stuff across the ocean. Okay, so if it's out of limits, you may say, well, we can just leave this home and go flying without it. But we want to be able to carry everything if we can. Now, if it's impossible to do, then again, you need to explain that and say, this is what we need to leave behind. We're just going to have to make 2 trips. Sorry, boss. But yeah, try to come up with a solution and show that your solution will be produce a safe flight. Okay. All right. So that's what we got. Good luck with that, and we will see you next time.